So our next speaker is Karoly from Budapest University of Technology and Economics, and he will tell us about random fractals.
First of all, I would like to say thanks to the organizers. I'm always very happy to be in Poland and also in Bedlevo. I like to mention that everything that is new is joined with Vilma Orgoványi. I usually use two projectors, but now there is only one screen, so I am experiencing with this kind of joint. If you are sitting too far and if you happen to want to see and you don't see, then please move closer. But I hope that it may work. What I'm going to talk about, these are kind of random fractal sets, and this randomness is generated by coin tossing. So imagine that we have this coin, which is a bias coin, as you can see. Hopefully you can see that on the left-hand side, there is James Madison, and on the right-hand side, this is the Liberty statue. And the probability that when you flip the coin, you get James Madison is P, and this P will be a very important parameter. And basically, the behavior of the random Cantor set will heavily depend on the value of P. So P is strictly in between 1 and 0. Okay, so that's why I need this to, I need to get used to this. But it is here. Okay. So what we do it is that there is another parameter which is capital M. In our case, capital M is equal to 3, and we divide. You see, well, I give the construction on the plane, so we divide the unit cube 3 square, and in higher dimension, in D dimension, 3 to the power D or M to the power D. So this is divided into 3 congruent parts, and altogether 9 squares, as you can see over there. And then we flip the coin. And when you see the strict face of James Madison, then it means that we retain those squares. And when the coin tossing results in the Liberty statue, it means that we are at the liberty not to work any longer on those places, and these places will be empty forever. So you see the face appeared in this position. So the first approximation of our random Cantor set, lambda 1, is the union of these orange squares, and then we repeat the same construction forever. So each of these retained square on the retained one are divided exactly m square, that is 9 congruent copies, and for each of them we toss the coin. So first we focus on this first square. What you see here, you see James Madison in the right bottom corner, and this L shape. That's why these squares are retained. This lambda 2 simply means that we are building lambda 2. And then you focus on the second square you see, and you toss the coin for the second square. Whenever you see James Madison at these places, you paint it to blue, and then we move to the third square. As you see here, this is James Madison over here, and Liberty other places, and this in capital L shape. James Madison yet again, and James Madison, these places you should keep them, and then finally there are only 3 Madison. So the union of the blue is the second approximation. So the first approximation was simply the union of the orange. This was lambda 1. The second approximation, which we prepared, then in each retained square, we repeated the original process independently of everything. Then the union is lambda 2, and you continue this process all until either everything disappears because it's possible, because this P is positive but strictly smaller than 1, is positive, yet you do not get so many squares. It's possible that you, with positive probability, you get absolutely no square, and that is what we call extinction. But you continue it as long as you can, in the ideal case to infinity, and whatever remains after infinitely many steps, it is our random Cantor set, which my God, okay, which we call random, which we call fractal percolation Cantor set. Okay. And then in the case when m is equal to 3, like here, and the probability is rather big, then you can see just the realization of this construction. So the idea is that the union, the collection of the squares which are retained at level n. So for example, the collection of blue squares when we are on the second level is E2, and the collection of orange squares was E1. So for every n, you take the cubes from En, and you take their union, and this union is the nth approximation. And this is a nested set of nested sequence of sets, a compact set, and whatever remain after infinitely many steps, it is the fractal percolation Cantor set. Now I will label this Cantor set. In most common cases, I just write lambda p. But if I want to, and in many cases, I just fix the dimension. The dimension will be fixed always. Many cases, I just fix m. And if m is fixed, then I don't write anything. I just write lambda p. There will be no misunderstanding about that. And then extinction is the event when the set becomes empty, and because it has positive probability, that's why all results that I'm going to state are always conditioned on non-extinction. Now, what is the Hausdorff dimension of such a set conditioned on non-extinction? What we do it is that now D on this picture, D is equal to 2, and usually D, for a while D will be equal to 2. So if D is equal to 2, and we come back to our picture earlier, then when m is equal to, so we have m square, little squares, m was 3, so we have 9. And the probability for each of them to retain is p. So this is the expected number of little squares which are contained in any square of level n contains m squared p little squares at average from the next generation. And that is why the Hausdorff dimension, which is equal to the box dimension, is the logarithm of this expected value divided by the logarithm of the inverse of the contraction, because this is the contraction almost surely conditioned on non-extinction. This is the Hausdorff dimension. What does that mean? For example, if we are on the plane, as we will be many times, what we need it is that, well, if this m squared p is smaller than m, which happens if and only if p is smaller than what? Smaller than 1 over m, this means that the Hausdorff dimension of lambda, or it's bigger to say that if this is bigger and if this is bigger, then the Hausdorff dimension of lambda will be bigger than 1. This will be an important condition. In order to arrange that this is non-negative, we, for example, on the plane need that m squared p is bigger than 1, that is p is bigger than 1 over m squared. So basically, on the plane, we always assume this, because otherwise we don't have any chance to end up with anything but the empty set. Okay. Now, what is that? I would like to tell you some older theorems. In order to do that, we will need the notation this definition of the orthogonal projection. So what is the orthogonal projection? Everybody knows what is orthogonal projection, but this is the way as we denote it. So we take an angle theta, and then this theta lambda is the orthogonal projection to this line. And there is a very, very famous theorem in geometric measure theory, which is the theorem of Marstrand. And this theorem says that if you have a set on the plane, so we are on the plane, and if you have a set whose dimension, Hausdorff dimension, is not bigger than 1, then for almost every direction, the orthogonal projection preserves the Hausdorff dimension for almost every projection. Now, if you have a big set, a set whose dimension is bigger than 1, then of course you cannot possibly preserve the dimension by projection, just because if your set has Hausdorff dimension 1.5, then the projection on the line cannot have Hausdorff dimension more than 1, so it will decrease. But the theorem, this fantastic theorem, says that if the set is big in this sense, then the projection is big, at least for Lebesgue, almost every direction. For Lebesgue, almost every direction, the projection is big. In which sense it's important? In the sense that the Lebesgue nature of the projection is positive. It does not say that for every direction, and it does not speak about interior point in the projection. And that's what we are going to do a little later. So we just go further. We consider the situation. So this was the Marstrand theorem. Sorry, I need to learn. This is the very first time I do this. So our theorem with Michal Rams, which was proved quite a few years ago, says that if P is bigger than 1 over M, so P is bigger than 1 over M means that the Hausdorff dimension is bigger than 1. So if this means that whenever the process does not die out, so lambda P is not the empty set, then almost surely the Hausdorff dimension is bigger than 1. This condition is equivalent to what I wrote over there. So if the dimension is bigger than 1, then for every, as opposed to the Marstrand theorem, not only almost every, but for every direction, for every theta, the projection is big, not only in a sense that its measure is positive, but the projection does contain intervals. And that's because somehow this randomness organizes this set lambda in such a beautiful way that we can get a much stronger result. One more time, for almost all realization, it's important that the order, for almost all realizations, you fix this realization, and in that realization, for all angle, the projection contains interval. The way as we popularize it, many of you have seen this as we normally popularize this, that if P is not very big, I would not like to get into how big P, but if P is not very big, then this lambda is going to be a random dust. So it's a totally disconnected set. And this totally disconnected set, so P is bigger than 1 over M, because otherwise you don't have a chance, because if P is smaller than 1 over M, then the dimension is smaller than 1. And if the dimension of this set is smaller than 1, then the projection is smaller than 1, and then you do not get an interval in a set whose dimension is smaller than 1. So we do need this assumption, but if this assumption holds, which guarantees the Hausdorff dimension of this random dust, this lambda is going to be a random dust, and if the Hausdorff dimension is bigger than 1, then although this is a random dust, if you take any time and the two-dimensional sun shines like this, then in the shadow you will find interval. And when I spoke about this theorem here in band level, then it was Felix who asked or made a comment that sun is not two-dimensional, and what can we do in the case if, for example, the sun is three-dimensional? And then we extended this theorem with my, in that time, student, Lajos Vágó, who went to Morgan Stanley now, but he was my student. And then we proved that everything which is stated here, I mean, the corresponding statement remains valid in any higher dimension.
With this picture, we made a poster at Impan, advertising Impan. The title was "From wherever the sun shines, we find a shadow."
So this picture, and then what did I? So here is the summary. If P is terribly small, what I said, P is terribly small, then you will end up empty-handed, nothing remains. And here is the first typo. What I wanted to say, that P is not terribly small, but small. Then in every direction, the dimension is preserved. I forgot to mention that not only that part of the Marstrand theorem, because the Marstrand theorem consists of two parts. You see that if the dimension is big, then in general, what you can expect that for almost every direction, the projection has positive measure, but we proved that for each, not almost every, but for all direction, the projection has non-empty interior, and the Marstrand theorem says that for almost every direction, the projection preserves the dimension in this area, and here we proved also with Michal Rams that the dimension is preserved for all, not for almost every, but for all direction. And this is basically written here as a summary. So this is the past what we did long ago, but then I started to be interested in what happens if you add a certain amount of inhomogeneity. What I mean it is that all until now what we did in the construction, if we go back to the very first part, that it was the square that we considered, all the little square, we have the liberty to choose or throw away any of them. But what happens if you repeat exactly the same construction with the difference? You see this P over here, but the center is not chosen. You are prohibited to retain the center. I could say that what you get, it is the random Sierpinski carpet, because if P is equal to 1, then it is the Sierpinski carpet, and this is the random Sierpinski carpet. So the center is for sure thrown away. So you do not throw, you do not flip the coin for the central place. You consider it as if it was the Liberty statue always, and you flip the coin all the other states. This is the only alteration. This is the inhomogeneous construction. Do you have any question? Do you understand what the construction? You don't have the center ever, and otherwise you do what you have done. Now, if you do this, then how many squares you have? Not 9, but only 8. And each of the squares, so you have 2, and each of them are retained with probability P. So what is the assumption that the host of dimension, which is given by this formula, is bigger than 1. This is bigger than 1 if this is bigger than, so P is bigger than 3 over 8. B is bigger than 3 over 8 is the if and only if condition for having host of dimension bigger than 1. And then in the previous case, what we proved with Michal Rams, it was that if you are in a situation that my God, it's here, yeah. If you are in a situation that the P is chosen so big, in this case, so big that the host of dimension is bigger than 1, then the projection in every direction contains an interval. So if you consider such an inhomogeneous construction, the same idea remains or not. So if you choose P so big that the Hausdorff dimension is strictly bigger than 1, whether or not you still have an interval in every direction. And it was long ago, it was published in the proceedings of the Banach Center, that there was, and so we published this result that actually no longer true. So if you give me any number, 1 million, then I will be able to choose an epsilon such that if we choose this interval 3/8 and 3/8 plus epsilon, and if you choose P from this interval, any P from this interval, then there will be 1 million angles such that the projection in those 1 million angles, this will be rational angles, tangent alpha rational angles, that the projection in those 1 million angle will not contain any interval. So you give me a number, let me see, you give me 1 million, then depending on 1 million, I can construct an epsilon such that for any probability from this interval, why is this interval interesting? Because P, it guarantees that the Hausdorff dimension of the random set is bigger than 1, but I have 1 million direction in which the projection is going to be with no interior point. So if you have such an inhomogeneity, then the situation is different. So this was pretty much like the introduction.
Excuse me.
Yeah.
What about the measure for these cases?
Oh, this is what I am going to talk a little bit.
Okay.
This is the only thing what we discovered with my former student, and now this is the new. This is what I would like to talk about now. So whatever starts, it is the new stuff, and this is joined with Vilma Orgoványi, and here is the paper on the archive. But if you like, you can find it on this QR code also. So what we do it is that this is the situation. I hope you understand that we never choose the person in the middle, but otherwise we run the same construction. And then there is something which is a little kind of inconvenient. This will be the only technical part of the talk, because what we want to do it is that we need to assign a certain matrices, a certain set of matrices to this iterated function system. Let me tell you what is in behind. I don't want to get into probability theory, but when you consider merely the Mandelbrot percolation case, that is, every little square can be retained with probability P. No square is doomed to death, let me say, like now the center one is killed for sure. There is no, so if in this original traditional situation, the probability background is the trivial, very well-known Galton-Watson process. What does that mean? Basically, every individual gives lives according to the same distribution to individuals, and the only thing you ask, what is the expected number of children? Because everybody gives according to the same, what is the expected number of children? Now, if you take the projection in this situation, the situation is much more difficult because we work with a branching process of multi-type in a random environment. And in this situation, we do not have a number which is the expected number of children, but we have expectation matrices which govern everything. And our goal is to produce these expectation matrices. This is what we are going to work now. I would like to, so this will be a little bit kind of technical. So what we do it is that we consider this iterated function system. I'm sorry, but we start counting always from 0. Apart from the cases when we start counting from -1, we almost never start counting from 1. And we use the notation, and in this bracket, it means the set 0, 1, 2, and minus 1. I use this notation always. Okay, so these are the so-called, so these are the intervals which in our case triadic intervals, but we start to count them from -3 for some reasons. So for example, you see here the level 1 intervals like that are from 0 to 3 and from 3 to 6. So and then these two people, as it is written, J0 and J1, are the so-called basic intervals for us. And using these basic intervals, we draw these 6 stripes, what you can see on this picture. And then we build up our matrices. The matrices are built up here, and I hope it does not take more than 5 minutes to talk about that. So how do we build up our matrices? This is this red one, this red equation is the definition. How many matrices do we have? We have 3 matrices because this is 1/3. If it was 1/4, then we should have 4 matrices. If 1/2, we should have 2 matrices. So now we have 3 matrices. That's why 1/3, that's why we have 3 matrices. And here is a kind of formula which is not inviting. So I just like to explain you why it is that this B1, this is B1, 0, 0, because we count the rows from 0. So the rows are numbered with 0 and 1. So B0, 0 is this person. Why this person should be equal to 2 as it is. This B1 means that we consider the central column. I don't know what is this column. Mark, could you tell me how do you call this color? This color. The color in the middle. What is the name of the color?
Which one is the middle?
Middle. This.
Almost white.
This.
J0.
Do you have any idea? Then middle color, whatever. So this person and this color, these two columns,
It's tan.
pardon?
Maybe it's tan.
Tan.
T-A-N. It's a light.
T-A-N. Thank you very much. The color 10 columns corresponds to B1. So when you want to fill in B1, you care only about color 10 columns. Now, when you speak about the first, this row, which we call 0th row, then we focus on this particular column. Now, in this column, you see that the first, what we call zeros basic interval is red, the one basic interval is black. And in this column, you see 2 reds and 1 black. And that's why you have here 2 and but you have here there 1. Now you go to the other tan, T-A-N, color column, and here you see 2 black, which 2 black, and that's why you have here 2, and only 1 red. This person is red, and that's why this is 1. So this is the formula which governs. But if you want to understand this formula, it is written down here. So what we do actually it is that we have to assign a set of matrices which will be the expectation matrices. These matrices needs to be multiplied by P, and you get the expectation matrices, and everything is governed by the expectation matrices. Okay, so for example, why is it that B1 1 0 well I think so this is the explanation. It takes some time, but it's completely logical how we assign a finite set of matrices to every situation. Then this situation depends on the set itself and the angle. We always project in rational angle, so we always assume that tangent theta is rational, is a rational number, because otherwise we could not get these matrices. Okay, so So this was one example, and I would like to show you the deterministic right angle Sierpinski triangle. This is also a similar carpet. We always kill the right top corner. So this is the deterministic. We do not choose, like in the Sierpinski carpet, we killed the central one. Here we kill the top right corner always, and on the remaining ones we just run the same process which provided us with the Mandelbrot calculation. And then in this situation we would like to find out what are the matrices. So for this situation, what are the matrices? So what is big zero? Zero means that we consider either this column or that column. Do you see what I show? Either this what I show or that what I show. Either. And when you take this line, I mean the first one, then we are here. And in here, you see this is J0, this is J1. And here, what we have, this 0, 2, so this is the left part, and that's why we have this one. And there is no right part here, so that's why it is 0. And if we come here to this column, then in this column there is this left part. This is left part, and then here what I show you in the red. When you get this, how do you get the red? You take the similar copies of the 0, 4, and 1/2 contraction, it goes to 1, 3, and then the image of the blue comes here. Okay, so the image of the blue. So here in this column, you have the image of a left part and the right part, and that's why you have 1, 1. So this is the way to assign matrices to such construction. But we need to realize that we don't need this projection construction if you just have an appropriate iterated function system that I will define later on the line. Then you can actually have a similar construction. Like I would just like to show you. You see why I desperately need two projectors. So this green is what you see over there, and then the red is in the middle, and the blue is on the right hand side. Now you take your coins, and then the strict looking face of James Madison tells you that we need to retain these two people. And the liberty means that you don't need to work anything in this because this is discarded. So we go further with this one and that one. And then for this one, we yet again flip the coins. This is the liberty. It means that you throw it away, and the Madison, you retain it. And here in this red, you yet again throw the coin. This is Madison, you retain these two people, but liberty, you discard it. And then in this way, you can get without any projection this set. So I just wanted to show you the first, if I can, the first approximation, the union of these two big people, and the second approximation, the union of these 4 people. Okay, so this is the construction, and the generally what we consider is what we get as a result of such a, not necessarily, we don't need, we will consider this kind of sets, but they can be, but they are not necessarily the projection of a carpet. Our assumption is that iterated function systems on the line are of this form when Ri is the contraction, and we always assume that the contraction is a reciprocal of the same integer, which is a positive, at least 2 integer. So all like 1/2, 1/3, and things like that. And the translation is a rational number. But if we multiply by a positive number, then nothing interesting happens. That's why we may assume that actually our system is of this form. So not only that T is rational, but T is a non-negative integer, and some further condition can be imposed just by multiplying with appropriate number. So that's basically what we assume in the future, that it has of this form, but it is not. And then the matrices are constructed as we have discussed. Okay. Now, when you have this deterministic system, then you prepare your coin tossing random Cantor set, this coin tossing algorithm as described, and what you get, the random set is lambda. And now we need some definitions. I'm referring to these matrices. So if you have this finite set of matrices, we call it good if all elements are non-negative. Allowable, it means that in each column and row you have non-negative element, positive element. And then this is a most important condition, that you are able to find an n, and you are able to find a finite word of length n, such that this product has only positive elements. This is an important condition, but this condition holds for all the set of matrices we found. So the really important condition, there exists an n, and there exists an n length sequence of this theta, such that if you multiply, theta is not the angle here, just the index, and you take this multiplication, then in this particular matrix, all entries are positive. Otherwise, all entries are negative, but you can find this is the definition of the good set of matrices. These are the matrices we can work with. That's why we say it's good. And here is our first theorem. I think I should kill this. Okay. Here is our first theorem with Vilma Orgoványi, that we take the Lyapunov exponent. I should have, just a moment, let me check where is the definition of the Lyapunov exponent. It's here. So we compute the Lyapunov exponent. It is completely naturally defined from this matrices B. So you compute the Lyapunov exponent, and if this Lyapunov exponent is bigger than e to the power negative lambda, then the Lebesgue measure of the attractor is positive. If it is smaller than equal to, then it is 0. So probably I answer your question here. So in our case, how do you compute the Lyapunov exponent? That is not so easy. Actually, we can do it only on the trivial cases, but unfortunately, Mark Polycott and Polina Vitnova were so nice that they computed for us for the right angle Sierpinski gasket. They computed, if you don't remember what was right angle Sierpinski gasket, maybe I can show you again that the right angled gasket was this. And in this case, where is that? It's here. This was the right angle Sierpinski gasket. And the 45-degree projection, these were the matrices. And for this set of matrices, Mark and Polina were so nice that they computed us that the Lyapunov exponent in this interval, which means that if P is bigger than the 0.6 whatever, then the measure is positive. Almost surely condition on non-extinction. Okay, and then what about the interior point? If you want to understand something about the interior point, then you need to consider the so-called lower spectral radius. So you have this set of matrices, and you consider for a given n all lengths of on n length product. You take the norm 1 over n, because this is n, so raised 1 over n, and the infimum for all n and for all products. So very much the infimum. And then you let n tends to infinity, and this person over here is the lower spectral radius. In some cases, we can understand it relatively well. And then what we proved with Vilma Orgovani, it was that if P is smaller than the reciprocal of the smaller spectral radius, then lambda does not contain any interval, almost surely. We have stronger result, but I don't have time because I have 10 more minutes to say the smoke. This will be good enough now. So altogether, if you put together what I said, if P is bigger than e to the power negative lambda, when lambda is the Lyapunov exponent, e to the power negative lambda, and smaller than the reciprocal of that very strange thing, which is this, then you have what we call interesting interval, because in this situation, this is what we call interesting interparameter interval. In this situation, you have positive measure for this and no empty interior. I would like to mention that there is a beautiful open question related to self-similar sets of the line. The question which is still open is whether or not there exists such a set with positive Lebesgue measure and empty interior. In higher dimension, there exists, but nobody knows whether such set exists on the line. And we will show a lot of examples of self-similar, random self-similar set when we have positive Lebesgue measure and empty interior. This is what I would like to do now. So I just go to this place. So for example, it is not difficult to compute for our old friend, the right-angled Sierpinski carpet, that this is going to be 1, but I show you. So in that case, this interval, but this yellow interval I show you, this yellow interval is an interesting parameter interval for the 45-degree projection of the rectangle carpet, meaning that if you choose P from this interval, then the Lebesgue measure is positive and the interior is empty. Okay, but we cannot ask always Mark and Paulina to compute us this lambda, and without that we cannot do anything, or we could not do anything, all until 1 year ago, because then we learned that Tom Rush, there is going to be a postdoc of Mark, yeah.
He's at Warwick at the moment.
Okay, so he had a beautiful theorem which helped us, and then we can answer many cases whether or not there exists such an interesting parameter interval. But in order to do that, we need the definition of the topological pressure. So what we do it is that we take this n-fold product, raise it to a power q, and then we take the exponential logarithm rate of this sum. This is the pressure function. I believe most of you know the pressure function, and I have only 6 minutes. Now I just need to say during the 6 minutes very few words about matrix cocycles. Sorry, I'm going to be very, very fast. Matrix cocycles and actually one-step matrix cocycles are this kind of products, basically. I'm sorry, I cannot be much more. And then there are 2 technical conditions, pitching and twisting. I have 5 minutes or 6. Cannot really say what it is. Technical condition related to the matrix cocycles, and if both of them holds, then there is something what we call pitching and twisting. Technical condition what we checked in all cases when what I will mention. So here's this marvelous theorem of Tom Rush. He says that if you have consider one typical, and now I show you because maybe some of you still would like to see it. This was the definition. Hopefully it's here, 1p, whatever. So if you consider one typical one-step co-cycle, then corresponding pressure function which we defined is either an affine function or it is strictly convex. This is very, very important for us because let's just have a look at how does it look like and put it into context with something that we proved with my student Vilma Orgovani. So it says that is strictly convex around zero. And why is that good? Because we prove that if the negative part of the pressure function is not like this, so if the pressure function is like the green, but not like the orange, because the orange is a straight line. So if the pressure function is not, it is definitely not like this, then there is an interesting parameter interval. So there is a parameter interval so that if you choose P, then you have positive Lebesgue measure and empty interior. So if you put this thing together, what we proved, it actually says then in our case, when this is true only unfortunately for, it was proved only unfortunately for invertible matrices. So you have invertible matrices for which you can check this one typical condition. And then from our theorem, it follows that there is an interesting parameter interval, which means that positive measure we know. And then here are examples when it holds. Here are examples. So one example is this. Let me tell you, 1 over x. So the 1 over 2 is the contraction ratio, and the translations are what? This is one cylinder interval. The translation is 0. This is another cylinder interval. The translation is 1. This is another cylinder interval. The translation is 2. And this is the last cylinder interval. The translation is 4. 0, 1, 2, 4, but not 3. If you take this, then the appropriate matrices are these ones. And for this, they are one typical. And that's why in this situation, we have interesting interval. Or you take 0, 1, 3. The translations are 0, 1, 3. One cylinder interval, the second cylinder, the last. Then the matrices are like this. And they also satisfy this condition. The matrices are invertible and the systems are one typical. So in both systems, we have interesting parameter intervals. And during the remaining 3 minutes, let me go to higher dimension. And this will be interesting, I hope, for many of you. So just go back to the beginning. What did we do when we wanted to construct this, originally this Mandelbrot percolation set? Here, we choose independently the squares. Now we do not choose squares because we have this 4 by 4 and then it is divided, but we do not choose the squares. What happens is that, for example, I would say that by coin tossing, you choose or you discard the left bottom corner of the squares, but these squares have big size and they heavily overlap. So if you happen to choose this corner and then this is half-half, then certainly for the first approximation you have chosen this. But then here is another possible left bottom corner, and it's possible that you have chosen this square also. So they are very much overlap. So this is an overlapping construction. The 0, 1, 2, 0, 1, 2. There are altogether 9 possibilities that you choose, but each of the squares are big squares, not this square of size 1/4, but square of size 1/2. So they are big squares, lots of overlappings. And this is the, I don't know which 5th or 6th approximation. And because of the overlapping, there are points which are very heavily covered. And then in this situation, remember that when we consider anything like that, then what we had it is that I'm not talking about the projection. I'm just talking about the set. The set has always housed of dimensions smaller than 1. So this original one could never ever have positive could never ever have a positive Lebesgue measure. By the way, these are the appropriate matrices. And what we have got, it was that in our situation, so when you take this two-dimensional example, which was over there, then if P is bigger than this number, then the Lebesgue measure of the attractor is positive and empty interior always. So we do not have any interior, and but if P is bigger than this number, then the Lebesgue measure is positive, and that cannot happen in the normal percolation, because then the host of dimension is always small, and this is 56. Thank you very much.
Thank you. So are there questions, comments?
Yes.
So geometry aside, how does the probability affect the topology of the Mandelbrot percolation set? For example, can we say if the probability is small, then it's totally disconnected, or if it's
Yeah. This is what I didn't have time to say, that there is a critical, in the normal traditional Mandelbrot percolation, there is a critical probability. If P is smaller than that, then it is totally disconnected. If P is bigger than this critical probability, then there is a pass somehow in between the opposite side with positive probability, only with positive probability, not conditioned, almost surely conditioned non-extinction, but with positive probability. If P is big, then you can go from one side to the other with positive probability. If P is small, it's totally disconnected. Yes.
Questions? If not, let's thank Karoly again. We have 22 minutes coffee break.